Today we're going to start off by talking about inverse functions and one-to-one functions, what those all mean. The first is a basic definition of one-to-one. All right, we talked about the definition of a function earlier, which was that for a relation to be a function, each member of the domain could be paired with only one member of the range, right? For it to be a function. Now, for a one-to-one function, or a relation to be one-to-one, not only does that have to be true, but each member of the domain must be paired with only one member of the range, and each member of the range must be paired with only one member of the domain, right? So I shouldn't have two values of x paired with the same value of y. So for instance, let's look at functions that might or might not be one-to-one. So this function right here is a function, right? That's just your basic parabola. Probably shouldn't have that. It's sort of misleading because it turns out this one's not going to be one-to-one. But this is just a basic function. We know it's a function. It just doesn't violate the horizontal line, or sorry, the vertical line test. It passes the vertical line test, so it's a function. However, if I drew a horizontal line like this, with this red line right here, we see that any horizontal line drawn, in that general vicinity, is going to intersect the function in more than one location. And what that means as far as the sets are concerned is that this value of y right here, this value of the range is paired with two different members of the domain. So because I can draw a horizontal line and have it intersect 2 points in the function, it fails the horizontal line test, and therefore the function doesn't fit the definition of being one-to-one. Right? So it is a function, but it is not one-to-one. So if we have a function, we want to know if it's a one-to-one function, we can use the horizontal line test to determine that. Now a function that would be one-to-one might be a function like, well, any linear function is one-to-one, right? Because I can draw a horizontal line anywhere along this linear function, and I'm never going to touch more than 1 point, so that one is one-to-one. And just once again, I'm not going to get too much into this, but just suffice it to say, any function that passes the horizontal line test is one-to-one. Okay, that's pretty much what you need to know. And the reason that's important relates to inverses. All right? Basic inverses of functions. Right, an inverse is a relation or a better way to let me start over. To find the inverse of a function, we must swap the domain and range of the function. Whoops. All right, so to find the inverse of a function, we must swap the domain and range of the function. And so an example of that would be if I start with the function f of x is equal to, let's say, 1 over, or let's say 2 over x plus 3. Right? And I want to find the inverse of that function. So what it means by swapping the domain and range is swap all of the independent variables and the dependent variables, right? And so really we can start by just calling f of x y, because we know that f of x is just a fancy way of saying y. And then we're going to go ahead and we're going to swap the domain and the range, swap x and y. So now we actually have the inverse function. We just want to solve it for y. All right, so to solve for y, that's going to involve doing what, do you think? What should we do to solve for y in this case? If we want to solve for this variable down here, we should start by doing what?
Multiply both sides by y.
Yep, multiply both sides by y plus 3. Clear out your denominator. And then divide both sides by. And then subtract 3. Right? So there we have the inverse function right there. And we could write this as a rational function by combining this into a single fraction, so we get 2 minus 3x over x. Right? So that function is going to be the inverse of 2 over y plus 3. So on the next page here, let's go ahead and graph both of these and see what type of relationship they have to each other. So the two functions were f of x is equal to 2 over y plus 3, and the inverse, which we notate f to the negative 1 power, just means that's the inverse, right? I can actually write this. Was 2 minus 3x over x. So let's go ahead now and graph those with our calculator. Although it's important to note, oops, sorry, I made a mistake here. This should be x plus 3. But it's important to note that these are rational functions, so we should be able to mostly graph them. In fact, let's just go ahead and do that. Probably makes more sense. So we know that our first function here, 2 over x plus 3, is going to have a vertical asymptote at x equals negative 3, like we talked about last week. We know that it's going, because of the multiplicity of x plus 3, it's going to be one of those ones that goes in from one side it approaches positive infinity, from the other side it will approach negative infinity. So let's go ahead and draw a dotted line for that. We know because the function on bottom is higher order than the function on top that the horizontal asymptote is going to be 0. That's going to be the end behavior. And it is going to not have any x-intercepts, right? It's never going to cross the x-axis because the numerator 2 can never be equal to 0, right? So it's not going to have any x-intercept. Its y-intercept is going to be, if I put an x equal to 0, the y-intercept is going to be 2/3. So it's going to cross like right there, meaning the function is going to look roughly like this. So there's that function right there. Our other function here, right, 2 minus 3x over x is going to have a 0 at 2/3. Right, when I plug in, sorry, it's going to cross the x-axis at 2/3, which is, we'll say is right here. So this was 2. Just going to recap here really quick. So in any case, we see the line y is equal to x here. Essentially, our inverse function here is a reflection of our original function over the line y is equal to x. Now you can imagine that if I reflect over the line y is equal to x, this 2/3 y-intercept, if I reflect it over there, will become 2/3 x-intercept. This vertical asymptote right here, if I reflect it over that line, imagine folding a piece of paper along this line, will become a horizontal asymptote. This horizontal asymptote, if I reflect it over, will become the vertical asymptote we have over here. And so everything horizontal becomes vertical, everything vertical becomes horizontal, everything in x or in y becomes an x, everything in x ends up in y. And as a result, the visual result of that is that it's a reflection over the line y is equal to x. And so all inverses are reflections over the line y is equal to x of their original function. If the original function here, first of all, is a function, and the new function is also a function because it passes the vertical line test. And it's also important to note that the original function is 1-to-1. It passes the horizontal line test, and interestingly, its new function passes the vertical line test. So that is not a coincidence. We're going to see in more cases that if the original function is 1-to-1, if it passes the horizontal line test, then its new function has to pass the vertical line test, and therefore it is a function. Whereas if we have a function that's not 1-to-1, it turns out its inverse relation will not actually be a function, which we'll see in the next example here. So a more basic maybe version of inverse functions is the function. We start off with a function like y is equal to x squared. Right? If I want to find the inverse of that, right, I can go ahead and just swap my variables. X equals y squared, and I get that x is equal to, I want to go ahead and solve for y here. And so I end up getting that y is equal to plus or minus the square root of x if I solve for y, right? And we know that plus or minus square root of x is not a function. So let's go ahead and graph both of these. This sort of drives my point home about the whole 1-to-1 situation. So the original function is just your basic quadratic, looks like that, right? And my new function, so this is x squared, my new function, square root of x, when I take the plus and minus, it's the top part and the, whoops. That looks really bad. Let's try that again. We get the top part and the bottom part. And so that is the function plus or minus square root of x. And so my original function, x squared, doesn't pass the horizontal line test. The new function, therefore, doesn't pass the vertical line test and is actually not a function because it doesn't pass the vertical line test. And they are still both reflection, or in this case, once again, the inverse is a reflection around the line y is equal to x. So that's the graphical implication of this. Okay? So if we want our new relation to actually be a function, our original function has to be 1-to-1. So one way we can get around that, if I want to find the inverse of y is equal to x squared and I want it to be a function, what I can do is I could just specify for x less than 0, right? Which would mean just this part right here. And if you imagine if I flip just this part around the x-axis, what am I going to get? I'm going to get just this part, the square root of x part here, the top, the plus square root of x part, not the minus square root of x. And so you can restrict the domain of a function to make it 1-to-1 so that when you take the inverse, you actually get a function and not a relation like this, which is not a function, right? And so then you would get that the inverse of this is going to be square root of x, just the top part, which is a function, right? So you can restrict the domain sometimes. Okay? Now, so inverses, we saw that in Algebra 2. I just wanted to review that. None of this should be hopefully new material, but the whole idea of 1-to-1 and domain restrictions might be a little bit new. So just know that that's a thing. The main reason we talk about this now is because our next example of a function and its inverse and so it's important to first of all realize that exponential functions are different from power functions, right? A power function, so this is an exponential function right here, and it differs from a power function in that a power function is a function where the base, right, is a variable and the exponent is a constant. In the case of an exponential function, though, the base is a constant and the exponent is a variable. And so when we say exponential function, we mean something very specific, not just a function that involves an exponent, but a function where the base is a constant and the exponent is a variable. All right, so that's the difference. And so as a result, with a power function, if we want to find the inverse, we can just take a root, right, to get rid of it. But if I want to find the inverse of this exponential function, if I go ahead and I start with y is equal to a to the x, and I want to find the inverse, I swap my variables, but I have no algebraic way of solving for y. Right? Oh, and by the way, the basic, an exponential function looks a lot different from a power function too. I probably should talk about this first. It sort of only climbs in one direction. It's not symmetrical like power functions are, where they climb or they grow at the same rate in both directions. A power function only grows as we go to positive infinity. As we go to negative infinity, we end up having a horizontal asymptote there. It never crosses the x-axis. It just goes down to 0. Okay. In any case, so that's the thing about exponential graphs is they're very basic. Also, anything raised to the first power is equal, to the 0 power is equal to what? Because when we cross the x-axis, x is 0. When we cross the y-axis here, x is 0. Anything to the 0 is equal to 1. So these all have intercepts of 1. So a to the 1 is always equal to, a to the 0 is always equal to 1. So the y-intercepts for all of these exponential functions, regardless of what a is, are always 1. And other than that, that's, you have a horizontal asymptote. It grows really quickly to the right, and that's generally what an exponential function looks like. They're pretty simple functions. They don't do a whole lot of stuff, unlike rational functions, which can be kind of crazy, and polynomial functions, which can also be kind of crazy. Exponential functions are pretty easy and behave very, very nicely. So in any case, we start off with an exponential function. We want to find the inverse of an exponential function, right? We swap the variables, and then we realize that, well, there's no way of solving algebraically for y like there is in the case of a power function, where I can just go ahead and take the root to get rid of the exponent. Here, I can't take a root to get rid of that y. So we just essentially make up a function that we would have if we solved for y, if we were able to solve for y, which we call the logarithmic function, base, whatever the base of the exponent was, a of x, right? So that's just, if you have x equals a to the y, then y equals log base a of x. The base just tells you what the base of the original exponent was, and then you're taking the log of x, to get whatever y happens to be. Now, if we go by our whole graphical thing that we talked about, if I draw my line y is equal to x here, then if I reflect a to the x over this line y is equal to x, I will get the logarithmic function, which looks like so. Log base a of x. Right? So there are reflections over the line y is equal to x. So the x-intercept, or the y-intercept of 1 becomes an x-intercept of 1 for log base a of x. The horizontal asymptote becomes the vertical asymptote, just like we saw with those rational functions. So we just reflect it over that line, and so we have log base a of x. Okay? So, any logarithmic equation can be written in terms of an exponential equation and vice versa. So for instance, a really basic thing we want to be able to do is if I give you an exponential expression like y equals 2 to the x. Let me do it this way instead. Let's say 8 equals 2 to the 3. That's an exponential equation, right? 2 raised to the third power equals 8. How could I write that in logarithmic form? Right? Imagine, and remember, this is just y equals something to the x power, right? And so my base here is 2, my power is x, and that equals 8. So what should my log be? What would be the logarithmic form of that equation? What base should it be, first of all? 2. Log base 2 of 3? Or of 8, yeah, equals 3. So what this expression means here is 2 raised to the third power equals 8, right? Which is what log base a of x equals y means. If I raise a, because remember, in the original equation, we had a to the y equals x, and then when we solved for y, we got log base a of x. So what this whole expression means is a raised to the yth power equals x. So 2 raised to the third power equals 8. All right? And so I should be able to take any logarithmic equation and write it in exponential form, any exponential equation and write it in logarithmic form. So what if I had log base 3 of 27 equals, let's say, 9 actually. Log base 3 of 9 is equal to 2. How would I write that in exponential form? So what raised to the what equals what?
3 squared equals 9.
What?
3 squared equals 9.
Yep, 3 squared is equal to 9. So this is the logarithmic way of saying the same thing. So this means the same exact thing as this. It's just written in logarithmic form. It's solved for whatever the power is and not for whatever the result of raising that number to that power is. Right? So a log, this whole expression here equals 3, meaning the log itself equals an exponent of the power of the exponent. Whatever the exponent is what the log equals. The log is the exponent, essentially. Log base 2 of 8 equals the exponent 3. Right? That's how these things work. And so we can use that idea to solve basic algebraic equations that involve logs and exponents. So for instance, let's say I have the equation so we can use this idea to solve basic logarithmic equations, like for instance the equation 5 to the x equals let's say 125. Right, or we could solve the equation log base x of 49 is equal to 2. Right. So what we can do if we have an exponential equation or a logarithmic equation, and we need to solve for either the exponent in the exponential equation, or we need to solve for the base in the logarithmic equation. A really neat trick is just to always take the exponential equation and write it in logarithmic form, and vice versa for the logarithmic equation. So in exponential form, in logarithmic form, 5 to the x equals 125 is equal to what? How can I write that in logarithmic form? Log base what?
Log base 5. 25 is equals x.
So 5 raised to what power is equal to 125? Because that's what we're asking for, right? This one,
3.
because 125 is 5 to the 3, yes. Another way you can, so that's one way you can do it. You can just look at it and ask yourself the question, what power do I have to raise 5 to get 125? Right, and hopefully it's going to be a whole number. If it's not, then you can't do it without a calculator anyways. Another way you could do this is to take this and go, okay, 5 to the x, and then if you see 125 and you think, oh, that's a power of 5, write it as 5 to the 3. And what you can do here, sorry, I'm just going to fix this really quick. What you can do is go ahead, and if you have two exponential expressions that have the same base, that means the exponents have to equal each other, right? The only way that's true is if x equals 3. So you can think about it in whatever way you want, right, with the exponential equations. With the logarithmic equations, right, you can look at this one and say, well, what power do I have, or what number raised to the second power equals 49? You can probably come up with that off the top of your head, right? What number raised to the second power equals 49? 7. So you'd right away you'd just be like x equals 7. But let's say you had like a major brain cramp and you couldn't remember that. You could write it in exponential form. What would this be like in exponential form?
2 to the x equals 49.
X to the 2 equals 49? Yeah. And then you just go ahead and take the square root of both sides. And you get x equals plus or minus 49, but we don't deal with plus or minus 7. But we only deal with the positive bases. It's to have a negative base of a logarithm is sort of a weird thing. Just like having a negative base of an exponent is a weird thing, because if you have negative numbers, negative 7 squared is 49. Negative 7 cubed is going to be a negative number. Negative 7 to the 4th is going to be a positive number. And so exponential functions with negative bases are really bizarre because they flip back and forth. They're like very strange functions. And so we don't really deal with them. So we're just going to take the positive 7 for this one. So that's another way you could do it. And sometimes you won't have a number that's just a nice even power of 7 here. And so you might have to do it this way. What if you had, for instance, log base x of 28 is equal to, let's say, 3. Is 28 is is anything raised to the third power 28? No. So you're not going to be able to just come up with that one. So that's when you want to definitely use that strategy and say, well, x cubed equals 28 then. And therefore x equals the cube root of 28. And so then that particular strategy becomes really important because you can solve equations that you wouldn't necessarily be able to solve otherwise. Likewise, with a situation like this, right? Let's an exponential equation. Maybe you have like 7 to the x equals 83, right? And you're saying, well, 7 raised to any power is not 83. So how am I going to solve this? Well, once again, write it in logarithmic form. Log base 7 of 83, right? And in a little bit, I can show you how to. I'm going to show you how to use your calculator. In fact, why don't we just go ahead and do it right now? So log base 7 of 83, right? How would we calculate that in our calculator? Just like we would have to take the cube root of 28 in our calculator. Log base 7 of 83, if we want to get a decimal approximation, at least we have to use our calculator. And so let's go on the next page here. Because in your calculator, you have two bases. You have base 10, which if you just see log x and there's no base indicated, we call that common log, and that just means that it's log base 10. Log base 10 is used very frequently because our numbering system is in base 10. And so log base 10 is a very convenient log to use. The other one that you'll see is base e, right? That's called Euler's number, or the natural exponential number. And that one is also very common and shows up a lot in calculus. And so that's why it's also on the calculator. But that's it. We only have base 10 and base e. So on the previous problem, I said log base 7 of 83, I believe, right? And so to calculate, to actually be able to do that in your calculator, right, you're going to have to convert it. And so the conversion formula is if I have log base a of x, and I want to convert this to a new base, let's call that base b, right? That's going to be log base b of x over log base b of a. Right? So if I want to take one log and write it in terms of another log, I can use this formula. So I have log base 7. I don't have log base 7 on my calculator. I would want to convert this to either log base 10 or log base e. Let's go with log base 10. So this is going to be equal to natural log base 10 of 83 over natural log of 7. Right? And that we can plug into our calculator. And so log of 83 divided by log of 7 is just going to be let's say 2.27. Right. So anytime you need to get a decimal approximation, we can use the base conversion formula to be able to use our calculator to get that decimal approximation. Okay. Okay. Let's go ahead and look at some other examples of I'm going to just give you some exponential and logarithmic equations because you have enough now to be able to solve a lot of these. I'm going to have you go ahead and take a crack at them. All right, so all right. This first one here, my hint to you for this one right here is to get this all in terms of a single base. So you have one base over here and one base over here. Get it all in terms of a single base. Same thing with that one. And that last one you're going to have to be a little tricky about. But the first three, try and write both sides in terms of the same base and do some equating of the exponents. Actually, no, wait on the last one there. I realized that we haven't talked about some of the properties we need. Forget about that last one. But oh yeah, I'm gonna do this one. Also, let's take a look at this one right here. So log, whoops. That's not what I wanted. So replace that last one with this one right here. This one we can do just using the properties that we know so far. So go ahead and see if you can get those three, or those four. All right, so let's take a look at these now. So the first three here, the key is just to write them all in the same base. So we see in this first example here, 4 and 2 are both powers of 2, right? 4 is 2 to the 2. And we're going to leave that 1 minus 2x up there. Whoops. And 2 is just, well, it's just 2, so it's 2 to the 1, right? And so when we have the same base, we can then go ahead and equate those. Right, and then we just have a linear equation at this point. And so we'll end up getting, I'm going to go ahead and subtract 2 from both sides. So I'm getting -1 is equal to -4x. And so x ends up equaling 1/4 for that one. This next one here, same deal. Once again, that's just 2 to the 2. 1/2, though, is 1 over 2 to the 1, which is 2 to the -1, right? So remember, fractions can be written as negative exponents. That's important. And so we'll end up getting 2x minus 2x squared equals -1 when we do that equating, right? So we have a quadratic that we have to go ahead and solve by factoring. So we get 2x squared minus 2x minus 1 equals 0. And so we're looking for a factor pair 1 and 2, 2 and 1, and 1 and 1. That is a difference of 2, which we don't have. So it's actually not factorable. So we're going to have to go ahead and use quadratic formula, which I don't really have any room for. So I'm just going to say that go ahead and use quadratic formula. I think we know quadratic formula at this point. We don't need any practice with it. So you'd finish that by using quadratic formula. Right. This next one, these are powers of 3, right? We get 3 to the 3 times 2x equals 3 to the, and remember, when we take a power to a power, which is what's happening here, right? We have 3 to the 3 raised to the 2x power. I didn't mention that up there, but when we take a power to a power, we multiply, right? So we're going to have, this will be the same as 3 to the 6x, right? And over here we have 3 to the 3rd raised to 3x minus 4 power, and so we'll get 3 to the 9x minus 12. And so we end up getting 6x equals 9x minus 12 after we get the exponents to be the same. We get the basis to be the same, and then we equate the exponents. And so we get 3x is equal to 12, and lastly x equals 4 for that one, right? And this next one right here, what did you guys think? What was the best thing to do with this next one? What's our go-to backup if we're stumped? And we're looking at a logarithmic equation or an exponential equation. But particularly if it's a logarithmic equation, what's our backup? Write it in
Exponential.
So what is it in exponential form?
3 squared equals square root of x minus 2.
So 9 equals square root of x minus 2. Then we have a root equation. How do I solve that?
Square both sides.
So I get 81 equals x minus 2. So x equals 83. Okay. All right, why don't you guys take a break? All right, let's look at one more example of an exponential one that's a little bit more complicated, but it uses the same basic principle, which is this one. 8 equals 4x squared, or 4 to the x squared times 2 to the 5x. All right. How do you think we should approach this one? 8 equals 4 to the x squared times 2 to the 5x. What are 8, 4, and 2 all?
Bases.
So 8 is 2 to the,
3.
4 is 2 to the,
2.
and then we already have 2 here. So if they're all the same base, first of all, this is going to be 2 to the 2x squared times 2 to the 5x. What do we do when we multiply two exponential expressions with the same base?
Add the exponent.
We add the exponents. And now what can we do?
Drop the bases.
Yeah, just go ahead and equate. And so we end up getting 2x squared plus 5x minus 3 equals 0. I'm going to do a little fishbowl for that. 1 and 2, 2 and 1, 1 and 3. We're looking for a difference of 5, which we get from 6 and 1. So this will end up factoring as x and 2x. The 3 has to multiply the 2. The 1 has to multiply the 1. The larger one has to be positive. So we end up getting that x could equal -3 or 1/2. -3 or 1/2. All right, so those are our two possible solutions there. So slightly more complicated, but it sort of works off of the same principle. All right, so for some more advanced logarithmic equations, to be able to solve them, we need to know about some basic log rules. So there's a whole bunch of properties that relate to logs that relate back to the exponential properties, since exponential expressions and logarithmics are very similar. So properties of logs. Just going to run through them. We're not going to spend time with the proofs because we don't have time for the proofs. But for instance, if I have log of a times b, right? That's equal to log of a plus log of b. So with logs, when you have the log of a product, you can write it as a sum of two separate logs of those two factors. If I have log of a over b, that's equal to log of a minus log of b, right? And lastly, if I have log of a to the n, if I have log of an exponential expression, I can bring the exponent out front, n times log of a. So those are all important properties that we can use. Another one is if I have log base or log of a equals log of b, for instance. The only way that's possible is if a equals b. So if I have two logs of the same bases that equal each other, just like if I have two exponential expressions of the same bases that equal each other, the argument, which in this case is the a and the b part, have to also be equal. So it's very similar to the exponential one, where if we have like a to the, let's say a to the x equals a to the y, then x has to equal y, right? We just did that a second ago. This is the same idea with logs. If you have log it's the same base, that's key, of a equals log, same base of b, then a must equal b. So these are all properties that we can use to help solve logarithmic and exponential equations. So let's look at a couple examples here. So for instance, if I have log of 7x minus 12 is equal to 2 log x. And I'll give you one other one. If I have log base 6 of x plus 3 plus log base 6 of x plus 4 is equal to 1. Right? So go ahead and use these properties we just introduced to try and solve these equations. Okay, so let's take a shot at these. What property should we use for this first one, do you think? First off here, if I have this 2 out front of this log x here.
Log x squared.
Yep, take log of, bring that 2 on the inside, and so we end up getting that 7x minus 12 is equal to x squared. Right, and so we have a quadratic, so we get x squared minus 7x plus 12 equals 0. And that'll factor out as x minus 3 times x minus 4. So x could equal 3 or 4. Now, let me ask you this question. Do both of those work in that equation? And yeah, sorry, it does appear that both those work. So sometimes we have to be careful with logarithmic equations because sometimes we'll get, especially if there's a quadratic, we'll get an answer that doesn't actually work on the original equation. In this case, if we do 3 times 7 minus, that's 21 minus 12, that'll give me 9, so I'll have log of 9. And then over here, I'll get 3 squared, and that's going to work. So the moral of the story is plug both of these back in here to make sure they both work, because what happens sometimes is you'll get log of like a negative number. And we know that we didn't spend time talking about domain and range, but the domain of log is 0 to, x has to be greater than 0, right? So I can't plug negative numbers into log here. So if any of these yields a negative number for either of these logs, that means it's not going to work and we have to toss it. So we should always, with logarithmic equations, be careful to check our solutions. Once again, I don't really have space to do it here, so I'm going to skip that step for now, but be wary of that. Okay, the next one, what property do you think we should use here? Multiply, yep. So log base 6 of x plus 3 times x plus 4, right, equals 1. And 1 is 6 to the what, do you think?
0.
Oh, I'm sorry. So let me take that back. 1 is 6 to the 0, but what can we do here? We have log base 6 of x plus 3 times x plus 4 equals 1. We have a logarithmic expression, and anytime we don't have logs, in this case, because we have logs on both sides, we do the whole equating thing, but now we don't have a log on this side. So if we just have a log equals some number, we always usually write it in, yeah, so 6 to the 1 equals x plus 3 times x plus 4, and 6 to the 1 is just 6, and if I multiply this out, I get x squared plus 7x plus 12. And so I'll get x squared, and then I got to go ahead and subtract the 6 plus 7x plus 6 equals 0. You can sort of see that 0 a little bit. Let's try that again. All right, so plus 6 equals 0. And so we want to go ahead and factor that. So x plus 6 times x plus 1. So x equals negative 6 and negative 1. Now in this case, we got to be careful. Now if we look at the original equation here, if I plug negative 1 in, negative 1 and 3 is positive 2. That's okay. Log base 6 is positive 2, and there's no problem there. If I plug negative 1 in for this one, I get positive 3. That works. So negative 1 seems to work. But what happens if I plug in negative 6? What's negative 6 plus 3? So then we're taking log of a negative number, which we can't do. So anytime one of these ends up making the log of any of the original expression, any of these logs equal to a negative number, then we got to toss it out. So negative 1 is the only one that works there. It's our only solution. All right. So that's how we can use those log properties to solve those types of equations. Natural log. or the natural log and exponential function? So e is an irrational number, right? Go ahead and type it into your calculator right now. You have an e button all the way on the left there, e to the x, and just do e to the 1, right? That'll give you what e is. And it's about equal to 2.718, but of course it keeps going and it never repeats, just like pi. So e is very much like pi, and we can think of it like pi. Pi generally doesn't end up being the base of an exponential expression, but e often does. So the function f of x equals e to the x is just called the natural exponential function. All right, and just like, e is still a number, and so the natural exponential function looks very much like any other exponential function. Just looks like this, right? It has a domain of all real numbers, and it has a range of y has to be greater than 0, right? Because it has that horizontal asymptote. It never crosses the y-axis, and its inverse, of course, is log base e of x. But the thing is, we don't say log base e of x. Instead, we always just say ln x, which just means log base e. It's a sort of a compact way of saying that. And so log base e is like any other log. Looks very similar to any other log. Sort of has that same general shape. Its domain is x has to be greater than 0, and its range is all reals. Because once again, domain and range get swapped with the inverse. So e to the x and ln x are inverses of each other, and we want to use that idea in some cases to be able to solve this. But other than that, there's really no difference in how these work. All of the same log properties and exponential properties apply to e to the x and log base e to the x, ln of x. We call that natural log, by the way. Natural log. Okay, so if we see equations that involve e to the x or ln x, it's really simple to solve them using this. Add like e to the 1 minus x is equal to 5, right? And then pretty much with the e to the x ones, you're always going to have to use your calculator ultimately, right? Or if I had the equation ln x equals, let's say 52. Now with this first one here, e to the 1 minus x equals 5, right? If I want to solve for x, I have an exponential expression. I can't write it in terms of the same base on both sides, right? Because 5 and e clearly don't have a common base. So what can I do? What's my go-to? Write it in exponential form, right? What would this be in exponential form? Log base what of what equals what? What's the base? So it should be ln of what?
5
Equals.
1 minus x.
So I end up getting that, and then I can just solve for x, right? I get x equals 1 minus ln 5, and I can get the decimal approximation for that in my calculator. So negative 0.61 if I round. Now, conversely, with that second one there, if I have ln x equals 52, how can I solve for x? X equals, write it in exponential form. So what's the base? E to the
52.
equals x, right? So x equals e to the 52, which we can just use our calculator, e to the 52. And we'll get about a really enormous number, of course. 3.8 times 10 to the 22. Which is not surprising because we know that exponential functions grow very, very quickly. So this should really be more like a squiggly line. Big, big number. But that's okay. So that's it. When you see E or you see ln, just know that you're working in base E. But the same rules and the same strategies that you've used for all the other ones are going to apply there as well. As far as like exponential equations are concerned. There's some that are just a bit on the trickier side that involve even more sort of messing around with. Whoops. Should not be an equal sign. So 9 to the x plus 4 times 3 to the x plus 3 is equal to 0. So in this case right here, it's tricky because we have two exponential expressions that are part of this equation, right, here and here, but then we also have this constant. Now, 9 to the x, could I write 9 to the x and 3 to the x with the same base? Yeah, so it's 3 to the 2x, right? Now, does this look similar to any other structure of an equation that we're familiar with? Or we have something raised to double the power that we have this raised to, and then we have a constant at the end? It's sort of, it has the same pattern as a quadratic, right? The same structure as a quadratic. So how would we factor a quadratic? We solve it by factoring it, right? How could we factor this? What would be our first terms here? What would we multiply together to get 3 to the 2x? Is 3 to the x times 3 to the x equal to 3 to the 2x? It is, isn't it? So that's going to be our first terms there. Okay. Now, we're looking for our coefficient here is 4, and we have 3. So we're looking for a factor pair of 3 that adds up to 4, right? Which would be 1 and 3, right? So we end up getting 3x equals -1, or, sorry, let me back up here for a second. So we end up getting 3x plus 1 equals 0, or 3x plus 3 is equal to 0. We're going to find out really quickly that that's not really going to work. So we end up getting that. Can 3 raised to any power be negative? Yeah, exponential expressions, their range is y is greater than 0, so neither of these have a solution. So this one is just no solution. But that would be the solution. They're not all like this, of course, but that would be the solution process, is to go ahead and factor and set them equal to each other. So really, unless they're opposite signs, right? Unless this is negative, then factoring is going to result. I mean, it's going to result in there being no solution there. So this one doesn't have a solution, but that's okay. This process can be used in many different situations as well. All right. We know what the basic functions look like, but we should be able to do transformations of logarithmic and exponential functions as well. So let's say I have the function f of x equals log base 2 of x minus 2 plus 1, right? I want you to do the following. Go ahead and graph it. Find f of 6. Solve the equation f of x equals 4. Once again, based on the graph, solve the equation the inequality, where is f of x greater than 0? And then I would like you to find the inverse. All right. Okay, so go ahead and do those 5 things for me, please. All right, so let's go ahead and graph this now. So I'll draw our coordinate plane. The normal log, we know, sort of has a shape like so, right? Has an x-intercept, never crosses the y-axis, but it's going to get shifted to the right by 2 and up by 1, right? So its new x-intercept f of x equals 0 is going to occur at a different point in time now. But in any case, we want to go ahead and we want to shift it over by 2 and up 1. So our original x-intercept was 1, but we're shifting it over by 1, 2, and then we're shifting it up 1. So the point that was at, so our x-intercept that used to be right here is getting shifted over by 2 and up by 1, so that new point is going to be right there. So we know it has to go through the point 3, 1, because it used to go through the point, because log base 2, before you shift it, goes through the point 1, 0. All right, and its x-intercept, to find the x-intercept, we set the new x-intercept, which is probably not going to be a nice even number. We set this equal to 0, and so we want to know when log base 2 of x minus 2 equals negative 1. Whoops. All right, and so we go 2 to the negative 1 equals x minus 2. And so x ends up equaling, oh, well, 2 to the negative 1 is 1/2, plus 2 is 5/2. So actually it does have a nice even one. So 5/2, which is right here, is going to be its new x-intercept. So it's going to look roughly like this. And its new, because it shifted over by 2, its horizontal asymptote is now, which I'm going to do that in blue actually, its horizontal asymptote is now the line x equals 2 instead of the line x equals 0, right? So it's never going to cross that horizontal asymptote there. So that's roughly what it's going to look like right there. All right, so we want to find f of 6. F of 6 is just going to be log base 2 of 6 minus 2 is 4. 4 is just 2 squared, so log base 2 of 2 squared is what? 2. So we get 3. F of 6 is 3. Solve f of x equals 4. So solve the equation log base 2 of x minus 2 plus 1 equals 4. So we'll end up getting log base 2 of x minus 2 is equal to 3. And so 2 cubed equals x minus 2, right, if we write it in exponential form. And so x ends up equaling 10. So that's the solution to f of x equals 4. And so that means it goes through the point 10, 4, right? So the point, let's say the point 10, 4 is like somewhere up here, because it has to go through that point if f of x equals 4 has a solution of 10. So that's the sort of graphical implication of the solution of f of x equals 4. Solve f of x is greater than 0. Where is f of x greater than 0? We found the x-intercept, right? We found where it's equal to 0 down here. So it's equal to 0 there, and then it's above 0 from there forward. So what's the solution going to be? It's going to be greater than 0 from 5/2 all the way to infinity. Right, so by solving this equation and figuring out what the x-intercept was, we know that it's above the x-intercept to the right and below to the left, so that means all the places where it's above is 5/2 to infinity. And then the inverse, let's do that in the next page. Y is equal to log base 2 of, x minus 2 plus 1. To find the inverse, let's go ahead and swap them first. And then we'll go ahead and start solving for y. So now we're going to have to go ahead and once we get log base 2 of y minus 2 equals x minus 1, let's go ahead and write it in exponential form. And then lastly, we can go ahead and add the 2. And it makes sense, right? It makes sense that the inverse function, right, is an exponential function based on what we know about their relationships to each other. Okay, so there's the inverse. And hopefully they should be, if we were to go ahead, I'm not going to spend time doing it because we're running out of time here, but if we were to graph this, this would be a reflection of the original function f over the line y is equal to x, right? All right, I know we're running low on time, but I want to just go over one last thing here. All right, so we're going to call it quits for today. We're going to talk about exponential word problems tomorrow, but your homework for tonight is the following. It is the Chapter 5 test. You probably have a similar one in your book, but I photocopied and scanned and sent out the one from the older version. And from that particular version, I would like you to do numbers 1 through 20 all. And that covers most of the exponential log inverse stuff right there. And then tomorrow we'll finish up so you can do those last 3 questions, 21, 22, and 23. And this is from the new handouts. And there will be a Chapter 4 test coming up pretty soon, and I promise by the end of the day today I will have the Chapter 2 solutions out. I'm going to start working on that right now. Have a great day, everyone.